Okay, so for this problem, we've been asked to find out the magnitude and direction of a resultant displacement vector if a little robot's gone 30 centimeters in the x direction and 20 centimeters in the y direction. So first thing we've done here is we haven't been told which direction x is actually, but we're just going to show people what we're assuming. So we're going to assume as normal x is horizontal and y is vertical as shown on the page. So if all else fails, what we can do here is we can just draw a scale diagram, and then we can just measure the different lengths, and we can use that to figure out the forces. Yeah, sorry, the displacements. So I'll use each 10 divisions is equal to 5 centimeters. And I'm going to draw my x and y components. So that's the vectors in the x and y direction. I'm going to do those in red. So we're going to go 5, 10, 15, 20, 25, 30 centimeters in this direction. And then we're going to go 5, 10, 15, 20. Oh, it was only 20. So let's bring that back to 20. 5, 10, 15, 20 centimeters in the y direction. Okay, we need to show people which way we're going. So it was going positive. It hasn't mentioned anything about going in the negative direction. So it's going 30 centimeters in the x direction, 20 centimeters in the y direction. Just write down the distances. So displacement is a vector. Distance is the magnitude of a displacement vector. So it's what you call a scalar. It doesn't really have a direction. So the magnitude is a distance. So 30 centimeters and 20 centimeters. Now, if we think about what this little robot's actually doing, so it's traveling in this direction for 30 centimeters, and then it turns around. Sorry, I can't turn this around, but then it goes 20 centimeters in this direction. It ends up here. So it ends up here. So starts here, finishes up here. The resultant vector is just the vector that joins the start point to the finish point for all of your displacement vectors put together, what they call nose to tail, so one after the other. So very nicely done. So my ruler can only do single degrees. We'll get it as close as we can. It's about as good as we're going to get. Okay, so the displacement vector is that vector shown in black. So like I say, one way we can do that is just to measure it and then use our scale. So from the scale drawn, let's just see what we've got in terms of displacement. So we have got 5, 10, 15, 20, 25, 30, 35 and 2 small divisions. So 10 small divisions makes 5. So 2 small divisions is going to make 1. So they've asked for magnitude, so let's write it in terms of magnitude. Magnitude of, let's write disp for short, disp vector. So displacement vector is equal to 36. We're working in centimeters, so centimeters. And the direction of displacement vector, so just the same thing, so just use quotes marks for that, is, and I'm going to just change these, so it's 34 degrees, but just bearing in mind this is just a scale drawing, so we're just going to say approximately. Now that kind of highlights one of the problems of using a scale drawing to do this, is that your results are just going to be approximate, just as accurate as you can measure them. If we want to get better results, we need to use our trigonometry that we talked about in the last week, in week 1. So in this case, we need to decide, are we going to use Pythagoras? Are we going to use SOHCAHTOA, sine, cosine, and tangent? We've been given 2 sides, and we've checked, and we've got a right angle. If we didn't have a right angle, we can't use either of those rules. And so 2 sides, we want the other side, so we want to use Pythagoras. So first thing we do is to label the sides. And so the longest side is called the hypotenuse, and for Pythagoras, we would usually call that C, and then we'll just call the other ones A and B. It doesn't really matter which is which. So we'll call this one A, this one B. So write down the formula. I'll just say using trig because we used the scale drawing before. Okay, we've got c squared is equal to a squared plus b squared. So we could substitute in the values, or we could just, we know we're going to need c in the end, so we're going to have to take the square root of both sides. We'll just do that first. Doesn't really matter which order you do it in. A squared plus b squared. So c is going to be equal to the square root of 30 squared plus 20 squared. So it's going to be equal to, and just need to get the calculator out. So we want to find the square root of 30 squared plus 20 squared. It's 36.06. So 36.06 centimeters. Now we want three significant figures, so we'll just say 36.1 centimeters. We were in centimeters. A pretty good idea that we got the right answer because that's pretty close to our scale, what we got from our scale drawing. Okay, so now we've got C, but we also want to find the direction of that resultant vector. So the direction will be given as an angle. It could be from the y-axis or it could be from the x-axis. It's up to you. In our case, it's going to be easiest to calculate an angle that's inside the triangle. So we'll take it from the x-axis and we'll go anti-clockwise. Well, it is anti-clockwise. So this is an angle, so we'll call that theta. So we've got to decide what we're going to use again. So we've written on the Pythagoras letters so far, but for the sine, cos, and tan is what we're going to have to do now because we're trying to find an angle. And so for sine, cos, and tan, we'd call the hypotenuse h. This time we do have to be careful. So that's our angle here. And so this side is adjacent to that. So that's going to be A, capital A for adjacent, and this side is going to be opposite. Okay, so we're trying to find out this angle. We probably want to use the two magnitudes that we've been given in case we've made a mistake calculating the hypotenuse. So that means we're going to use opposite and adjacent, so it's going to be tan. So tan, sorry, wrong color. So tan theta is going to be opposite over adjacent. We'll substitute our values. Tan theta is equal to 20 over adjacent is 30. So theta is equal to inverse tan of that, tan to the minus 1, 20 over 30. Remember, you can also call that a tan, but we'll call it tan to the minus 1. So therefore theta is equal to, so this little calc pad I think uses a tan. And one thing, again, we're just checking, it's definitely in degrees. Yep. So 33.7 degrees. And this agrees pretty closely with what I can't measure more accurately than 1 degree with my ruler on this in OneNote. But it's close enough to be confident we've got the right answer. So we've pretty much, well, we have checked both of these. We still want to write out the answer just to save you a bit of boredom. We'll copy that across. All of these out and we'll put in the right values. Okay, so writing the answer in full. Magnitude is 36.1 centimeters and the direction is 33.7 degrees, but don't leave it at that. Anti-clockwise from the positive x-axis. Okay, you got to be a little bit careful. So if you got x in this direction, just color doesn't really matter. But suppose you had x going this way, So, and you've said it's 33.7 degrees. The person reading it doesn't know that you don't mean this. So he doesn't know that or she doesn't know that your vector's heading down this way. So you've got to be careful to specify what direction from the x-axis, clockwise or anti-clockwise. Just forgotten to underline it so we can find it easily. And then we're done.